So I want to thank the people who've worked with me on this. Before I start, the first half was done in collaboration with Brett Geiger at High Point University, and then the second part was done with experimental labs at Johns Hopkins University. That's Jim Knierim, Noah Cowan, and Ketchen Zhang. And I also want to thank NIMH for funding this work. So I want you to imagine for a second that you have to navigate from one place to another, and your phone ran out of battery, so you don't have Google Maps. And think about the sorts of strategies you might use. The first might be kind of self-localization, so you look around at the landmarks that are around you and try to think about where you are in relation to familiar landmarks. The second may not be quite as obvious. You're probably not going to be continually looking at these landmarks as you move. So maybe more on the subconscious level, you know what direction you're moving in, you know about how fast you're going, and you can update your internal sense of where you are relative to where you started from. And this is something we call path integration. It's something that rats and mice and other animals that we do these studies with have been shown to be very good at. And the basic idea is a calculus idea that we want to update the internal estimate of position by integrating over self-motion information like the velocity. And then of course, errors are going to accumulate as you do this path integration. And so you need an error correction step as well, where you again kind of periodically look up at landmarks to correct for any errors in the path integrator. Today I'm going to focus my talk on the second step of path integration. When we go to models of path integration, this is kind of a typical general form that you would see. Here I'm looking at a PDE, so I've taken the limit as the number of cells goes to infinity. U, the state variable, represents the synaptic input for this cell with preferred spatial variable X. That spatial variable could be the heading direction, it could be absolute location or place, it could be phase if this is a model of say, grid cells. So there are many different things it could represent that would be biologically relevant. F of U is the firing rate of each cell. And the firing rate is convolved with this weight tuning curve, W of X. This is the weight between cells with distance X between their preferred spatial variables. B is a tonic drive. And then H is the self-motion input. So this could have terms in it with the velocity, with possibly the acceleration of the animal. But importantly, this cannot contain absolute location. So nowhere in this model does the system get information about absolute location or about landmarks. These are generally considered to be continuous attractor neural networks. So the idea here is that the weight W of X is going to be kind of the center surround connectivity, where these are the outgoing weights from the cell in the middle to the other cells on the sheet. And the weights are set such that when this cell is active, it wants to recruit its neighbors to also be active, and at the same time inhibit cells further away from being active. And this results in this localized activity bump shown here in color over the cellular sheet. This activity bump I'll call capital U. It can be located anywhere. This X hat could be anything over the cell sheet. So X hat is typically the center of mass of the bump. And because you could shift this activity bump anywhere, this is called a continuous attractor because it has a continuum of attractor states. Right, so for a path integration model, it has two components. The first is translation invariance of the activity bump. And really this is saying that we want the path integration model to lie in the larger class of continuous attractor neural network models. So the idea here is that when you have a self-motion input as the animal is moving, that the activity bump should be translated across the cellular sheet without any mutations. The second component, in order to have perfect path integration, there should exist a constant gain factor, G, such that the velocity of the activity bump is equal to G times the velocity of the animal. In many models, G should be 1, but that's not necessarily true. The important thing is that G should be constant in time. There's a nice mathematical paper from back in 2012 that showed that in order to have perfect translation invariance and perfect path integration, the self-motion input should be multiplicative in nature. In other words, it should have this form where the velocity is multiplied by some function of the state. For our system, the model would look something like this. Notice here that G, this gain, is an independent parameter in the model. It does not depend on the other parameters, such as your weight tuning curve. And to think about how this model works, we consider this whole thing to be an effective weight. And so instead of just having this even weight tuning curve here, the system learns this effective weights that is proportional to the gradient of W and scaled by the velocity. So that when the animal moves left, because of these weights, you see a shift of the activity bump to the left, and the opposite happens when the animal moves to the right. So one more thing on this slide, this model works beautifully mathematically, and because of that, there are numerous mathematically analysis studies that use this model to look at things like robustness to noise. But there are some issues with it in terms of how biologically realistic it is. So how realistic is it for the system to learn the gradient of the weights and for those weights to be scaled on the time course of the animal's velocity? So because of this, many models, particularly those that are based in numerical simulations, use an additive self-motion input of this form. So importantly, this H now does not depend on the state U. It's not possible to get path integration with an additive model if one just has one group of cells. And so what people typically do is to have two groups of cells. The weights are shifted. No longer do we see the gradient vector, but the outgoing weights from group 1 are shifted to the right by L, from group 2 are shifted to the left. And now the self-motion inputs are opposite here, so that group 1 is more tuned to movement to the right, group 2 is tuned to movement to the left. And so when the animal is moving to the left, the activity bump of group 2 is slightly larger than that of group 1, and that causes the activity bump to move to the left. And the opposite happens when the animal moves right. And one can extend this idea to two-dimensional space by having 4 groups of cells, one for north, west, south, and east. So while this model has been shown through simulations to do a very good job of path integration, there's not nearly as much of a mathematical foundation for these models as there is for the multiplicative model. And so we set out to provide a rigorous mathematical analysis of this model. And what I'll talk to you today is some of our results from looking at the shape of the moving activity bump, any intrinsic errors the system has, even when you don't have any sources of noise, and what parameters can minimize those errors. And maybe most interestingly, how does the gain depend on the model parameters? In the multiplicative model, the gain is an independent parameter itself, but here there's no explicit parameter for the gain. It depends in a complex way on all the model parameters. But before I go further, we changed slightly a definition that's typically used in the literature. Typically when people talk about a continuous attractor network with 2 groups, what they mean is that both U1 and U2 stay on the attractor. But for us, we define this translation invariance as the average activity bump remaining on the attractor. The idea is that a downstream network of neurons that wants to read out the encoded variable might get inputs from both U1 and U2, and so perhaps the average is more important than each group individually. And then we define 2 errors. First is the error in translation invariance. We denote this by V. And then the second is the error in path integration, which is the true gain minus this constant gain factor, which we define as the gain if we had perfect translation invariance. It's not a given that we could get a constant G naught even if V were 0, but we will show you a condition for which you do get a constant factor G naught. Okay, so this is just a reminder of our dynamical system. We begin our analysis with the ansatz that ui is capital U plus or minus G plus V. So we have an opposite effect and then a shared effect. To analyze the opposite effect, we look at the difference in the two states, and we find that G is flat spatially, and it tracks the self-motion input H. So to see how this works visually, in this simulation, we start with U1 and U2 both at this equilibrium bump capital U, and then we apply to it a constant velocity input, and we see group 1 gradually increasing to U plus H, while group 2 decreases to U minus H. Here we compare U plus G to U1 and U minus G to U2, and we see right away that this term G is much, much larger than this shared term V. V is the difference between the solid curve and the dashed curve in both, so it's very small relative to the size of the activity bump. I'll return in a minute to talk more about V, but first let me talk about how we compute the gain. I don't have all the mathematical details here, but the idea is that we do a Taylor expansion of this, considering G and V to be small perturbations. And then we use linear operator theory to get this expression for the gain. We find rho G over tau V plus this O of H squared error term. So H is again that self-motion input. It should be fairly small relative to the size of the activity bump itself. What we found is that this error is 0 when V is 0. So this is an error entirely dependent on the errors in translation invariance. We have this new term here, this rho factor, which is given by this quotient here. The brackets indicate the L2 inner product. Given a constant velocity, our G, the opposite effect, should converge to H, which is alpha V. And so we find this constant gain factor G naught is rho alpha over tau. That's just what this term becomes. And so before we consider a time varying velocity input, let me just show you some examples. So here I look at 3 of the most commonly used weight tuning curves. The black is a cosine, the red is Gaussian, and then the green is a Mexican hat function. The cosine and Gauss are often used for head direction cells or place cells. The Mexican hat is based on a simplification, a 1D simplification of a grid cell network. And here are the 3 equilibrium activity bumps for these 3 weight tuning curves. I set the parameters so that they would all have about the same peak value. Some example trajectories. So this is a smooth velocity, but it converges to a constant. Here, when the H is 0.1, that's about 15% of the peak of the activity bump. So pretty large compared to what people usually consider. And we still see very good agreement between the black, which is the actual trajectory, and the X hat, which is the encoded spatial variable. When we look at the errors, we see they're pretty small, about 2% for translation invariance and up to 3% for the gain. Okay, so moving on to a time varying velocity input. If we go back to this gain equation, we see that we have this G of t divided by V of t. And in order to have G naught as rho alpha over tau, we need G to be alpha V. So going back to this equation and using integration by parts, we find that our equation G looks like this, where it has this alpha minus beta term here. And so we conclude from this that ideal path integration, in order to have that constant G naught, requires a balance of velocity and acceleration inputs, or beta equals alpha. So this is really an interesting result. It's not one that we expected. In the multiplicative model, the ideal path integration requires no acceleration input whatsoever. And in the additive models, typically people use only a velocity input. So this was a surprising result. And I'm going to go through these slides rather quickly, but just to show you an example, I gave it a sinusoidal velocity input and then compared what happens when beta equals alpha. You see exact agreement. When there's no acceleration input in blue, you see this lag of the encoded spatial variable behind the true. And we can get an exact analytical expression for the phase shift and for the different relative error and amplitude of the response x hat compared to the true y. Okay, so what is an explicit expression for the gain? In other words, how does the gain depend on the model parameters? We found that we could simplify this under the condition that WD convolved with f prime of u is proportional to u prime. And looking at this expression, you'll see that minus rho will be that constant of proportionality. To determine when this condition holds, we did some Fourier analysis and found that the condition holds if and only if this expression holds for all n greater than or equal to 1. And looking back at our 3 examples, that really depends on the decay rate of these coefficients w hat. We find that it holds exactly for the cosine because it only has 1 non-zero Fourier coefficient. It holds approximately for the Mexican hat and not at all for the Gaussian. So the condition really depends on how broad or narrow the weight tuning curve is. For the example of the cosine weights, the parameters we're interested in are m, the scale factor of the weights, the shift parameter L, and this tonic drive B. And when we follow through with this Fourier analysis and simplify, we get this explicit expression for the gain. There is a term R here, which is the radius of the bump, but we find that this equation holds well even if we hold R constant. That's this dashed red here. So we find that the gain is inversely related to the tonic drive B, is roughly linear in L, and decays linearly in M. And we have similar expressions for the Mexican hat tuning curves as well. Okay, for the sake of time, I'm gonna skip this slide. This looks at the spatial properties of that function V. And this concludes part 1 of my talk. This is part of the results we've had from this rigorous analysis, and the gain itself, this intrinsic error, is O of h squared. And we find that this error in V is O of h squared when that condition 1 holds in particular. And we've derived an explicit expression for the gain. The next thing I want to talk about is some numerical simulations I've done with a path integration model of grid cells using that Mexican hat tuning curve. And the predictions I've made for a particular experiment that my collaborators are running. So they call this thing the dome, and the idea is that as this animal, as this rat moves around the dome, they project cues up in this virtual reality environment, and they control the cues as a function of the animal's movement. And what they've been able to demonstrate with this experiment is that they can actually recalibrate the gain of the path integrator based on the experience within the dome. And so I've been working to develop theories of how this recalibration takes place. One big question is where it takes place. So one can imagine a recalibration in the upstream head direction cells or speed cells. Or there could be a recalibration within this grid cell network itself, which is typically considered to be the path integrator. So just considering those 2 alternatives, I've made some predictions for how we could differentiate between them. So the idea here, on the top here, we have this, the population activity pattern of all the cells in this 2-dimensional array. And as the animal moves, the self-motion input drives this capital U in response to the animal's movement here in physical space. So this is the population lattice, and down here is the activity of one single neuron marked by this white asterisk. And every time an activity bump moves through the asterisk, you see that this cell is active. If I just fast forward to the end of this video, we see this nice hexagonal lattice in the single neuron response, similar to that of the population lattice. The gain of the path integrator defined as the speed of the lattice translations over the speed of the animal, can also be given by the period of the population lattice, this distance here, divided by the period of the single neuron response. Okay, so I'm gonna go ahead and start this video and then we'll talk about it. So this is the video you just saw on the far left. And on the right, I'm looking at two different things that could happen within the network due to the gain recalibration experiment. The first thing that could happen is that the network could change its perceived speed. It thinks that the animal is going twice as fast as it was originally, and so we see these translations have increased by a factor of 2 in terms of their speed. On the right, the speed of the translations is the same, but the lattice itself has compressed. This period has changed. And so here's what happens at the end of the movie. The interesting thing, these are two completely different mechanisms for recalibration. One is an increase in perceived speed. One is no change in perceived speed, but a compression of the lattice. And yet the single neuron response looks very similar. And this becomes even more complicated because we don't have access to the single neuron response. We have access to this undersampling of what we perceive to be the single neuron response, this undersampled hexagonal grid. And so we've developed some algorithms for inferring this full single neuron response grid pattern from this undersampled track, and made some predictions about how we can determine, distinguish between what's going on in the system when we get the data that they are going to be giving me as soon as the lockdowns lift up. So if a recalibration occurs upstream, there should be no change in the population lattice. And so for the single neuron response, we should see no change in pairs of coactive cells and no change in the relative phase of cell-to-cell pairs. But if there's a change in the spatial profile of the weights, that will decrease the grid period and lead to changes in both the pairs of coactive cells and the relative phase of cell-to-cell pairs. And finally, if there's a change in the strength of the weights, then that will not lead to a compression in the population level, but you'll see a smaller radius of each field. And so that might decrease the number of coactive pairs while having no change in relative phase of cell-to-cell pairs. And so this is where this partnership stands right now. I'm making predictions for what we would expect to see as they run this gain recalibration experiment and now record from grid cells in the MEC to try to see kind of these neural mechanisms. And the idea is once we get that data in and can test these various predictions and identify where the recalibration is taking place, we can go back to these attractor network models and modify them or adapt them to have some biologically realistic mechanism for the gain recalibration. So thank you for your time, and I'd be happy to take any questions that you have.
Lovely, thank you very much, Kathryn. So does anybody have any questions? Please either raise your hand or indicate in the chat. I guess I'll kick off if everyone's feeling a little bit Zoom shy. These three different underlying mechanisms for the recalibration, do you have a feel for which one might be the most biologically plausible, or would they apply in different circumstances? Are there sort of different causes for the recalibration?
Right. I can certainly tell you which would be the simplest. So that the simplest recalibration would be one that's upstream, although it's kind of just moving the problem further upstream and then saying, well, how do those cells recalibrate? The difficulty with recalibrating in the grid cell network is that these are attractor networks. And so if you have heterogeneities in the weights, you could lose this capital U, right? You could lose this attractor pattern of these hexagons. And so, you know, there are things I've been looking into in terms of how to make the system more robust to heterogeneities. This is something that a lot of people have looked at that would permit some sort of a change in weights. It seems like something of this form might be easier, just to change the strength of the weights as opposed to the spatial profile. So So just from a practical standpoint of how I would model this, it seems like this changing the spatial profile would be the hardest. But then on the flip side, when we were initially talking about this with the experimenters, we were talking about it a lot in terms of how the grid might compress. So the period of the grid is inversely related to the gain. And so one idea that people typically think about is that these different modules of grid cells that have different periods have different gain factors. And if we're changing the gain, we should be changing the period of the grids. And so that was kind of an initial prediction. And so the difficulties that lie in the modeling side and in trying to think of biologically realistic implementations don't necessarily mean that we shouldn't think about it and look for it.
Yeah. Okay, great. Okay, are there any other questions?
I can ask a quick question. Oh, you can hear me on there, right?
Yep.
So just to follow on from that, Kathryn, and firstly, thank you very much for a very nice talk. So do you have a feeling from the analysis about, I mean, you talked a bit about robustness, about how robust each of these different mechanisms are to noise or heterogeneity, or just in terms of the general overall stability of these patterns?
Yeah, so I didn't share that here. I have done some robustness studies, in particular for the Mexican hat weight tuning curve, because that is kind of the simplification of the grid cell model that I'm particularly interested in. So it is fairly robust to changes in L, this shift parameter, and in the strength of the weights. There are critical values where you see this kind of bifurcation and you lose the attractor network, or you see this dramatic change in the period when you change these parameters. And so I've been able to identify pretty well kind of the range in which you can change the parameters, and it certainly gives you plenty of room to have some significant changes in the gain. Maybe not as significant by themselves in what they're seeing in the experiments, but we need the data to know that. But there is also a complication when it comes to looking at robustness for grid cells. So this kind of gets into the weeds a bit. But whenever you have this attractor network, you can't have any sort of heterogeneities at the boundaries, because it will cause deformities throughout the entire cellular sheet. And so the easiest way to get around that is to have periodic boundary conditions. But if you have periodic boundary conditions, you're enforcing a particular rotation to have lower energy than other rotations. And so it forces the grid to not rotate. Whereas if you do other methods, like using some sort of an envelope function to kind of taper away the effects at the boundary, it's very prone to rotation. And so in general, it would be unstable in terms of a rotation of the grid. And that complicates things, since we are looking at kind of this circular track, and you might have a recalibration of head direction cells, a rotation might occur as part of the recalibration. And so that makes it complicated in terms of being able to read out predictions from the model in terms of what you'd expect to see in the system due to just lack of robustness versus due to something real happening in the gain recalibration.
Thank you very much.